Yeah, thank you very much for the kind introduction. The title of my talk is 3,264 conics in a second. And this takes us on a journey from 19th century geometry, illustrated by the left picture, to 21st century computing and data science, illustrated by the right picture. Everything I'm saying in at least in the first half of the talk, is contained in this article, called 3264 Conics in a Second. And this can be found in the notices of the American Math Society, January last year. On the cover, you see the same page, the same picture that we're discussing. And the artist added the galaxy. That wasn't me, but this is the source for a good part of the talk, and you can find this online. So let's start with conics in the plane. So by a conic in the plane, for now, I mean the real plane R2. And a conic is the set of zeros of a quadratic polynomial in two variables, x and y. So let's say A, capital A, is a quadratic polynomial with the 6 coefficients, A1, A2, up to A6. These are real numbers, not all zero. And for example, typical conic might be the circle in blue or the ellipse in green. Now let's say a second conic enters the scene, which are called capital U, which also has 6 coefficients, U1 through U6. Then these two conics, according to Bezout's theorem, will always intersect in 4 points. So you can see the blue conic and the green conic intersect in 4 points. And this is a special case of Bezout's theorem from 250 years ago. Now, to make this theorem actually true, we have to work in the complex plane, and we have to work in the complex projective plane. So complex, well, it could happen that if that of these 4 red points, not all 4 are real, but only 2 are real, or maybe 0 are real. If you slide the green ellipse to the right, then at some point there might be a tangency, then the 2 red points come together, they become imaginary. And if you slide the ellipse all the way to the right, then all 4 points become imaginary. And we will be interested in the next couple of minutes in the transition situation where we have a tangency. I should maybe say I cannot see the chat. So Jared, if there are questions in the chat, please interrupt me. So I'll try to go slowly. So if there's any question, type it in the chat. And Jared, I would ask you to interrupt me, please, with questions. Okay, so tangency. Well, when we count intersection points, then we're going to say we have a tangency, or an intersection point counts with multiplicity 2 or more, if in addition to the 2 given quadratic polynomials, also the Jacobian determinant vanishes. So recall A and U are the 2 given conics. Then I'd look at the Jacobian determinant, the partial of A with respect to x, times the partial of U with respect to y, minus the other product of partials. This is again a quadratic polynomial in x and y. And if this also vanishes, then the conic U is tangent to the conic A at that point. So we can say the 2 conics, U and A, are tangent if they exist, complex numbers, real or complex numbers, x and y, such that this system of 3 quadratic equations and 2 unknowns has a solution. Now we'd like to eliminate the quantifier. We'd like to express the tangency condition purely in terms of the 6 coefficients of A and the 6 coefficients of U. Well, we can do this using computer algebra. For example, the program Macaulay 2 that Praise mentioned that we studied in Ibadan a couple of years ago. So if we eliminate x and y from this system of 3 equations and 2 unknowns, we get a polynomial only in the a's and the u's, and this will be an expression of degree 12 that goes on for a while. It will be homogeneous of degree 6 in the A's and homogeneous of degree 6 in the U's. Now, this polynomial has 3,210 terms. So that's a lot of terms if you want to write them down by hand. And this used to be thought of as a big polynomial, but actually this day and age where we use computers, we talk about data science, it's not such a big polynomial at all. It's actually a small polynomial in 3,210 terms of degree 6 in the A's and degree 6 in the U's. This was known in the 19th century literature as the tact invariant of the two conics. So we have these two conics, the blue one and the green one, and they're tangent somewhere if the tact invariant vanishes, this polynomial. So this brings us to Steiner's conic problem, and this will get us to the title of this lecture. So Steiner asked in 1848, how many conics are tangent to 5 given conics? So I'm given 5 blue conics, they're given to me. For example, the 4 blue ellipses and the blue hyperbola. And I'm asking for all red conics that are tangent to the 5 given conics somewhere. Now, each tangency condition imposes a constraint of degree 6 on the conic, right? Which constraint? That constraint, right? So if A is fixed, then the condition on U is this small polynomial of degree 6 in the U's. So the vanishing of this polynomials in the U's says that the conic U, the red conic U, is tangent to the blue conic A. So we have 5 constraints. We also have 5 degrees of freedom, right? Because there are 6 coefficients in specifying a conic. You learned that in the seminar, you learned that we should work in projective space. So up to scaling, there are 5 degrees of freedom. In specifying a conic, we have 5 constraints. So we expect finitely many solutions to this problem over the complex numbers. Now, Bézout's theorem predicts that the answer is 6 times 6 times 6 times 6 times 6, right? Because we have 6 constraints. And so the answer should be 7,776. And this was proposed by Steiner in 1848. So that's a nice answer, except it's wrong, right? So Steiner's answer is incorrect. And the reason it's incorrect is that Bézout's theorem has certain hypotheses. So a warning to the students, if you apply a math theorem, you should really check the hypotheses very, very carefully before you apply your theorem. So in this example, Bézout's theorem actually does not apply. And the reason is that there are many, many extraneous solutions. There's 2 degrees of freedom, a surface worth of extraneous solutions, namely all the double lines. So what do I mean by a double line? Well, a double line is a conic whose defining equation is the square of a linear equation. So if you take a linear expression, constant x plus constant y plus a constant to the squared, then that has the property that the Jacobian determinant will always vanish. And that means that a double line is tangent to any other conic, and there's 2 degrees of freedom, a surface worth of double conic. So we have to take out this extraneous surface. And the question is, how much is left? Well, this was answered by Chalet in 1864, and he found the correct answer. The correct answer is the hero of the day. It's 3,264. Now, this kind of counting and circle of ideas was further developed by Schubert, a famous book on numerative geometry in 1879. This led to Hilbert's 15th problem in the year 1900. And in the 20th century, this led to enumerative algebraic geometry and intersection theory. So this error that Steiner made and the correction that was given by Chalet had a very important role in the history of algebraic geometry. There's also a book on intersection theory by Eisenbart and Harris from a few years ago that has this number prominently in the title. So what I like to do in the next 20-25 minutes, I like to combine the perspective of enumerative algebraic geometry that I set out to explain from the 19th century and then moving on to the 20th century. And from that perspective, the question is, how many conics are tangent to 5 general conics? How many complex conics are tangent to 5 given conics? And if you believe Chalet, the answer is 3,264. But today, in 2021, we can ask a much more interesting and much harder question, namely, using numerical algebraic geometry, we can ask the question, how do we compute all conics tangent to your 5 given conics? You choose your blue conics. How can you actually compute all the red conics that are tangent? So note the difference between the two questions. The first question is, how many solutions are there? And the second question that I see as important these days is, how do you find all these solutions to your data? Now, a word about the numerical algebraic geometry. So numerical algebraic geometry is much younger. It's tied to the development of computers. It's much younger than the numerative geometry. Maybe it started about 40 years ago, and it's concerned with numerical solutions to systems of polynomial equations. So here again is an instance. There are 5 given conics, and then in red, one of the solutions, one of the conics that are tangent to the given one. So this bunny, I'm given the ears, the eyes, and the mouth, and then the head is one of the solutions. So why is this a system of equations? Well, it's a system of equations because the instance of Steiner's problem, your 5 blue conics, are specified by 30 real numbers. So this is organized maybe as a 5x6 table of numbers, the coefficients A1, A2, all the way to A6. And those numbers specify the instance. Then for each letter A or B or C or D or E, you write down a polynomial in the unknown use. Which polynomial? Well, the tact invariant, small polynomial, with only 3,210 terms, and then you find the common solutions, 5 constraints, 5 degrees of freedom. Now, 40 minutes ago, I suggested that you start trying to do this yourself. So you do not need to download any software. So all you need is an internet connection, and you can go to this website that Diane put into the chat, Julia Homotopy Continuation org, DIY, do it yourself. And that's a web interface where you can find the solution. So you go to this website, the first thing you do is you choose your own instance of 5 conics, or you ask the system to give you a random instance. It's important to press the button plus 5 times. This fixes the conics. You can change the coefficients. Then you click the dark blue compute button, and then hopefully within a second, the answer comes out. So for this instance, in 0.99 seconds, we find that this was successfully solved. 3,264 complex solutions were found. Of those, only 44 were real, and 6 were ellipses, and 38 were hyperbolas. So on the website, it lists all the solutions, it shows you pictures, and as you scroll further down, you get more information about the solution. So this is an easy-to-use website that every high school student who has access to the internet can try out. Now, what's under the hood is a software called homotopy continuation.jl. JL stands for Julia, which is a software for numerical computing. So when you press the blue button, then this calls a session in homotopy continuation.jl. So this is an open source Julia package developed by Paul Breiding and Sascha Timmer, and you can use this in this web interface. If you have your own problem of solving polynomial equations, then you have to go further. You have to download and learn how to use the software, but it's very, very well documented, and this is very, very easy to use. Whoops. Are there any questions? Did you guys try this out? Okay, let's get real. Of course, in applications, the solutions we're mostly interested in are real solutions. And one question is whether all the complex solutions can actually be real. And this was proved in 1997. So this was discussed at the time. And the paper by Runge, Tonoli, and Wurst in 1997 gave a theoretical proof for the existence of 5 real conics such that all solutions are real. Right? So by that I mean, can you draw 5 blue conics in the plane such that all 3,264 red solutions are actually defined over the real numbers, and then necessarily they touch the blue conics at real points. Now, this proof was a theoretical proof, but this raises the question, can you find an explicit instance of given conics, capital A, B, C, D, E, such that the solutions are all real? And we described such an instance in our paper, and here's the solution. So here are the coefficient matrix. You choose the coefficients to be these relatively friendly rational numbers. The constant term is normalized to be 1. So this is a system of 5 conics in the plane. And I claim, and I'll show you the proof in a moment, that for this particular instance to our problem, all the solutions are actually real. All complex solutions are real. The idea behind the construction is based on a geometric idea called the Pentagon Construction. And the Pentagon Construction goes as follows. So you choose your given blue conics as follows. You choose each conic. You start out with 5 lines that make a pentagon, and then you double each line, and you rotate it around just a little bit in such a way that the intersection point of each pair of lines is somewhere in the middle of the edges of a convex pentagon. So imagine a convex pentagon. You look at the lines spanned by the sides of the pentagon, you double each line, and then you get this pair of lines, you get this pair of chopsticks that intersects somewhere in the edge of the pentagon. Now what you do, now you write down the equations and you wiggle the coefficients just a little bit. So then this will turn the pair of lines into hyperbolas. And you ask the question, what are all the conics tangent to such a particular configuration? And it turns out that that's the idea of creating a fully real situation. So what happens here is that a red conic can be tangent. So in the double chopstick situation, the red conic goes through the intersection point. This counts with multiplicity 2, and this can break up into 2 tangency situations, or it could be tangent at one of the 2 lines. So for each of the edges of the pentagon, either we can be a tangent to one of the 2 lines, or we have this a situation that arises from passing through the intersection point. And then as you work it out, you get 3, 2, 6, 4, and I'll show you this in a moment. In fact, there's an animation that shows the solutions, shows this instance and all the solutions also at the same website if you click at the bottom. Now, everything I said so far was really 19th century material and accessible at the undergraduate level. But we heard that there are some students here who are PhD students. We heard from students in Stellenbosch. We heard from students in Scotland. So I owe you a little bit of graduate level mathematics. So let me talk about how you would derive the number 3264 in a modern graduate class. So in a graduate class on algebraic geometry, you would learn about blowups. So the lady from Scotland mentioned that she's studying blowups. So what you would do is you look at the exceptional locus and you blow up this exceptional locus. So this is the surface of double lines inside the P5 of all conics. So you blow this up and you get an enhanced version of our P5. That's a 5-dimensional manifold called the space of complete conics. Now, this 5-dimensional manifold has a Chow ring or cohomology ring. And this chow ring, this intersection ring, is generated by two special classes, the class P for point and L for line. Each of these describes a divisor, a codimension 1 class. So P is the divisor of all conics passing through a fixed point. That's a codimension 1 condition. And L is the dual condition. It's the conics tangent to a fixed line. Now, the way a chow ring or cohomology ring works is that multiplication corresponds to intersection. So we're going to derive a couple of basic multiplicative relations that describe the intersection of these divisors. So, for example, P to the 5th, I claim, is 1. Well, why is that? Well, P is all the conics to a fixed point. P to the 5th is P times P times P times P times P. So we're intersecting conics passing to the first point with conics passing to the second point and so on. So P to the 5th is the number of conics that pass to 5 given points, and that number is 1. Now, dually, the number of conics that are tangent to 5 given lines by the same token is also 1. Now, if you look at conics that pass to 4 points and are tangent to 1 line, then there'll be 2 of them. If you have 3 points on 2 lines, there'll be 4 solutions. And then again, by symmetry, you can swap P and L. So this describes the intersections on our space of complete conics. This is the good space that we're going to work on. Now, the final ingredient that we need is the class of the conics tangent to a given conic. And that class is 2L plus 2P. And the best way to see this is to look at the leading term of the tact invariant. So by just staring at the tact invariant, with a little bit of practice, you can read this off, that the conics tangent to a given conics have class 2L plus 2P. So now what do we want to compute? We're going to compute C to the 5th. So we're interested in all conics that are tangent to 5 given conics. So C times C times C times C times C. So we note that this is 32 times L plus P to the 5th by just plugging in. Then we apply the binomial theorem. So L plus P to the 5th by the binomial theorem. Well, we get L to the 5th plus 5 L to the 4P plus 10 and so on, the appropriate row in the Pascal triangle. Then we substitute in the relations we derived 3 minutes ago. And then the parenthesis evaluates to 102. So 102 is the number of conics tangent to the 5 edges of our pentagon. We multiply by 32 and we get 3264. So this slide shows you how you would derive this in a graduate class. And unsurprisingly, this also gives you a hint at a numerical algorithm for finding the solutions, the stuff that's under the hood when you click the blue button. Okay, let me pause again and see whether there's any questions. I'm trying to go slow. We have lots and lots of time. So this modern derivation is sort of a formulaic way of thinking about this picture. Right? So this picture reduces our number to 32 times 102.
Perhaps I'll ask a question if that's okay.
Hi, yes,
Hi.
Go for it.
This thing that you just explained, was this Charles's original derivation, or did he have a sort of equivalent? I don't know if he knew about blowups, but did he
actually, I did not read the original source, I must confess. Schubert's book is full of derivations like this. So Schubert certainly knew this argument. I don't know whether Charles knew about this.
Thanks. I was just wondering if there's a kind of different thing which doesn't go through blowups, or I mean, the chow ring is of course implicit in a lot of things.
I think he must have done something like this.
Yeah.
But
and you kind of try to peel off the extra stuff. Yeah.
Okay, so let's talk a little bit about numerical mathematics. dynamics, right? So how do you actually numerically solve a system of polynomial equations? Well, underlying that, locally near root is always Newton's method. So in calculus, you learn Newton's method in one variable. If you're lucky in multivariable calculus, you learn it in multiple variables. And we're going to use that, of course, to talk about solutions. Let me give you a definition. A point, so a given a system of equations, I'm going to say a point is an approximate zero of a polynomial system if there is a nearby true zero to which the Newton iteration converges quadratic. So the charm of Newton's method is that if you are near a true solution, then you can show that there's quadratic convergence. And if you were in this nearby region, we're going to call that an approximate zero. Now, the thing about Newton's method is it's locally very, very nice, but it's globally a mess. So this picture just shows you the Newton dynamics for polynomial in one complex variable of degree 3 in one variable, one polynomial in one variable of degree 3. So such a polynomial has 3 roots, green root, a blue root, and a red root. And they're located right here in the center. Those are the 3 roots. And in green, blue, and red, we're coloring the plane according to what root we're converging to if we run Newton's iteration. So you see that near the root, there's very, very nice behavior. But at the boundary, it's fractal-like and chaotic. So there's a fractal chaotic behavior. So really here, there's fractal-like behavior in this dynamical system. So the global dynamics of Newton's method, even for a low degree polynomial in one variable, is very difficult and messy. But if you're nearby a true solution, then things are nice. And the problem with this definition is it's very hard to actually, you need to give a theorem to check whether something is an approximate zero. Now, this leads us to the concept of certification. So here's the definition again of approximate zero. The amazing thing is that we can verify in exact arithmetic whether a proposed nearby zero is an approximate zero. So this can be verified in exact arithmetic. So you start with the polynomial system. You, by any method whatsoever, you compute some numerical points that you believe are close to the true solutions. Now recall for the students, so when you take a class in numerical computing, people always talk about real numbers, but there are no real numbers in computing. You'll never ever see a real number. You'll be dead before you see a real number. There are too many digits. Every number that you ever see, every floating point number that you ever see is a rational number. So by some method, we compute nearby, what we believe to be nearby floating point solutions. The coordinates are floating point numbers, that is to say rational numbers, but you believe that nearby there's a true solution. This can be certified in exact arithmetic. So the state of the art of certification is this article called Certifying Zeros of Polynomial Systems Using Interval Arithmetic. And there's a implementation of this. So the input is numerical solutions found by any method, for example, by homotopy continuation. And the output is a symbolic proof that our fully real instance in this application is actually correct. Okay, so this is a proof. So let me emphasize this for the students in Ibadan and the faculty in Amsterdam. So the paradigm in computing and algebraic geometry for many years has been symbolic computing, and we believe the accurate behavior of symbolic algorithms, but there's a new paradigm that says that numerical computing is faster, it's accurate, and it's certified. It comes with the proof. So this method by Breiting, Rosa, and Tim is implemented in the software. So you can click an extra button that says certify, and with little extra time, you actually get a proof. So that's how we prove the fully real instance. So this is a proof that this is a correct instance, and it's described in the paper. So let me summarize. Grobner bases for many years used to be the main engine for computing in algebraic geometry. With today's numerical methods, one can go much further while retaining, and this is important, reliability and certified proofs. So what I've done so far is I've mixed geometry, algebraic geometry with numerical computing, and I gave you some hints that I see this as applied math. So a little bit of an advertisement. Just last week, we had a big, sadly, online conference or SIAM conference on algebraic geometry. There's a journal that I've been involved with called the Applied Algebra and Geometry Journal. So this gives you a little bit of the context where this comes from. These pictures show you different areas of application. So optimization, robotics, computer vision, applied topology, geometric modeling, tensors, and this is also semi-definite programming. And what I like to do now is I like to step away and take a slightly different perspective on the conics. So I'll pause for 10 seconds, and then I start the second half of the talk.
Maybe I'll ask another one if no one else asks questions. But so these numerical methods, are they kind of completely orthogonal to Grobner bases? So there's no Grobner basis that would go into the numerical methods, or would they kind of mesh together?
This particular code, this is orthogonal. This is independent. There are some approaches, so even if you solve with Grobner base, at the very end of the day, you do numerics and you do numerical linear algebra at the end. But this is a purely numerical method. So they're really complementary to Grobner base.
So this would begin with some kind of Monte Carlo and finding some stuff first, and then.
Well, maybe not Monte Carlo. This is so you're tracking these paths. You have a homotopy. You basically solve some system that you know how to solve, and then by an ODE tracer, you trace to.
Oh, because the starting point is so simple that you can just solve it explicitly.
Well, it's not so simple. You have to give it. This is part of the design. You have to give a starting point. That you have to design a starting point that then you can track.
Okay.
But
so the starting point must have some obvious solutions, basically.
The starting point, you have to start somewhere that you can rely on the solutions. Exactly. Yeah. Let me say, in solving, I mean, what are we doing at the end of the day? In the end of the day, in numerical computing, we're relying on numerical linear algebra, right? Numerical linear algebra is the powerhouse that drives science, technology, engineering. I mean, the world and Google runs on numerical linear algebra. What I'm trying to say here is that we should use, so something that's very dear to my heart, is that we should postpone the use of the power of numerical linear algebra as long as we can. We should really use nonlinear structures as long as we can, but at the very end of the day, we have to do numerical linear algebra. Even here, Newton's iteration, you have to deal with big matrices that you have to invert or, pseudo-invert. So numerical linear algebra is always in the background, even if you start with Grobner basis when you do solving. So I'm just saying this because I just posted something on the archive called Beyond Linear Algebra. So I see this sort of, consistent with the philosophy of going beyond linear algebra. But to answer your question, these numerical homotopy methods are independent of Grobner basis.
Thanks.
Okay, so to the students, we're going to start a new topic. So I'm going to tell you now about LSSM, linear spaces of symmetric matrices. So there's a triangle.
Maybe you should answer some question on the chat. What is the complexity of this numerical approach? So somebody wants to know what computation.
Okay. That's a very good question. So there is a big literature on complexity of path continuation that was started by Smale in the maybe 30, 40 years ago, and there were some recent advances. So there's a big literature. Summing up, the very simple version, it depends on how many paths you're tracking. So this number 3264 is really governing the complexity, but there's a big literature on complexity of numerical algorithms. And I suggest just Googling, complexity of numerical solving. Okay, so LSSM. What is this picture? Well, this picture is, again, now I'm looking at quadratic surfaces, and I'm imposing 9 tangency conditions on a quadratic surface. 9, because there's 9 degrees of freedom in making a quadratic surface in 3 space. So quadratic surface in 3 space has 10 coefficients for the 10 entries of a symmetric 4x4 matrix. And here in the blue picture, I'm requiring the quadratic surface to pass through 3 red given points, to be tangent to 3 black given lines, and to be tangent to 3 blue given planes. And the number of solutions is 104. Here I change the numbers. I take 2 points, 2 planes, and 5 lines, and the answer is 128. So you can imagine how this is felt. So conics, quadratic hypersurfaces, and the symmetric matrices that represent them are very, very important in optimization and statistics. And those are 2 fields that are fundamental for data science these days. So earlier in the chat, somebody from Somalia wrote that they're very interested in statistics, calculus, and algebra. So this part of the lecture is for you. So I'm going to write Sn for the space of real symmetric n by n matrices. So a real symmetric, so a symmetric n by n matrix has n plus 1 choose 2 distinct entries, the entries on and above the diagonal. So this is a real vector space of dimension n plus 1 choose 2, which I call Sn. Now there's a miracle about real symmetric matrices. And the miracle is that their eigenvalues are all real. This is one of my favorite miracles in mathematics, that if you take a symmetric real matrix, all n complex eigenvalues will actually be real. That miracle is known as the spectral theorem. Now, among those matrices, the ones that are most interesting to us are those where all the eigenvalues are strictly positive. And I'm going to write Sn plus for the set of these matrices. So these are matrices whose n eigenvalues are positive real numbers. Those are called positive definite matrices. Now this set is a convex cone, right? So it turns out that if I have a real a positive definite matrix, and Jared has another positive definite matrix, we add our matrices, it's still positive definite. So this set is convex, it's a convex cone, it's semi-algebraic, it's defined by polynomial inequalities, and this is the cone we're going to be interested in. Now let me also fix an LSSM, a linear subspace, and I'm going to write M for the dimension of this linear subspace. So L is a linear space of dimension M inside this ambient space. Now, the intersection of this cone with the linear space, if non-empty, is a convex cone of dimension M. Now, to draw a convex cone, it's convenient to slice it with an affine hyperplane. And in this manner, we get a convex body of dimension M minus 1. So this picture, and you saw this picture on the first slide of the talk, it's also the logo of our group in Leipzig. So this picture illustrates the situation for n equals 3 and m equals 4. So I'm looking here, this red yellow picture illustrates symmetric 3x3 matrices. So there's a 6-dimensional space. Then I have this 6-dimensional cone of positive definite matrices. I slice it with a 4-dimensional linear space. I get a 4-dimensional yellow convex cone, but then I cut this with an affine hyperplane, and I get this picture in 3 space. So in yellow, I have this object, that's the cone cut with the plane. It looks like a tetrahedron, a fattened up tetrahedron. It's sometimes called a samosa, the kind of thing you eat in an Indian restaurant. So the way you get this is you take a tetrahedron, you puff some air in it, you blow up a tetrahedron, these 6 edges remain edges. but otherwise it's a little bit round. Now in red, these the elephant ears is the rest of the cubic surface, right? So the boundary of this is given by the vanishing of the 3x3 determinant restricted to this four-dimensional space. So this is a cubic surface, and this illustrates the geometry of our intersection when n is 3 and m is 4. Now in optimization, these things are called spectrahedron. So this cone or this intersection is called a spectrahedron. These are the feasible regions in semi-definite programming. In statistics, these are called linear Gaussian models, right? So in statistics, the reason we're interested in positive definite matrices is because they are the covariance matrices of Gaussian distributions. So a Gaussian distribution on n-dimensional space is given by a mean vector, let's say the origin, and a covariance matrix, and that's a positive definite matrix. The inverse of the covariance matrix is also positive definite. It's the concentration matrix. And if we impose linear constraints on either the covariance matrix or the concentration matrix, we speak about linear Gaussian models. And those are fundamental in statistics and maybe of interest to the gentleman from Somalia. As I said, optimization and statistics are foundational for data science. And here with the objects I described, we have the corresponding optimization problem. So semi-definite program is the problem of minimizing or maximizing a linear function over the spectrahedron. So this is the cone intersected with an affine space. Now, a linear function on matrix space can be convenient, is often written like this. So S is the coefficient matrix, and I get a linear function by taking the trace of the matrix product. That's the dot product. That's a way of writing the dot product between a matrix S and another matrix S. It's the trace of the matrix product. Now, an optimization problem in statistics is MLE, maximum likelihood estimation. There, the goal is to maximize the likelihood function for a given matrix S. S is the sample covariance matrix of the data, and the likelihood function is the logarithm of the determinant. That's well defined because the determinant of the positive definite matrix is a positive number minus the inner product. And this is over the cone, over the linear model. Okay. And these pictures, this is another picture of a spectrahedron, and this is a picture of a mixture of three Gaussians for n equals 2. So from data science back to algebraic geometry, back to Hermann Schubert, who wrote this amazing book in 1879. So we can go on from our problem in the plane to our problem in 3 space. But let's first relate this to symmetric matrices. So in algebraic geometry, we can say, what can we now say maybe about 2 quadrics in the plane or 2 quadrics in P3? So quadric in P2, as we see, is a quadratic curve, but now we're thinking about this as a symmetric 3x3 matrix. A quadratic surface in P4, so here are 2 quadratic surfaces. We're thinking about each of these as given by a symmetric 4x4 matrix, 10 coefficients, 9 degrees of freedom. Now, what is the intersection of 2 quadrics in P3? Well, that's a curve. That's an elliptic curve. Right? That's a genus 1 curve. What's the intersection of 3 quadrics, for example, in P4? That's a genus 5 canonical curve. In P5, it's a K3 surface. So even by writing down just very few symmetric matrices, you get the full range of interesting algebraic geometric objects, from elliptic curves to canonical curves to K3 surfaces and so on. But coming back to the 19th century, we can ask how many quadratic surfaces are tangent to 9 given quadratic surfaces? What is the analog to 3, 6, 2, 4, 1 dimension higher? And the answer was found by Schubert. The answer is 606,841,088. And to answer Ballar's question, so this is from Schubert's book, so sorry, this is in German. So you carry out the binomial coefficient calculation that I did. Basically, it's a trinomial coefficient. Then you collect terms, and then Schubert concludes that the answer is 666,841,88. So that is, as I said, the 19th and 20th century. The question is, how many solutions are there? The 21st and hopefully 22nd century question is, how do you find the solution to your instance? So I showed you that in a lot less than 1 second, you can find 3,264 solutions. And I think a couple of years from now, the way things develop, a couple of years from now, we will hopefully be able also to reliably find all 666 million solutions. So this we cannot do today. We're not at this stage where we can solve polynomial systems with 666 million solutions, but I'm pretty optimistic that a couple of years from now, we will be able to do this. Now, the role that algebra can play for optimization and statistics, computations in these fields, is to give precision to the questions we're asking. And one question we can ask, what is the algebraic degree of these optimization problems? So let me recall, we have the optimization problem, semi-definite programming, and MLE. Now, these are problems whose input is a given matrix, typically the sample covariance matrix. And let's say this has rational entries. And the algebraic degree is the number of complex solutions to the critical equation. So the precise given rational data. So the data is the model. L is the model, the linear space. S is the matrix, the sample covariance matrix. Then the optimal solution has coordinates in Q bar in the field of algebraic numbers. And such an algebraic number has a degree over Q. And we could ask, what is the degree, the algebraic degree of this field extension? This, to answer the question that was asked 7 minutes ago, is an algebraic complexity measure of solving this problem. This is the true, intrinsic algebraic complexity of solving these important optimization problems, irrespective of method for using it. So this is the intrinsic complexity of the coordinates of the solution in terms of the data. Now, the LSSM project, which I like to describe in the remaining couple of minutes, started by some important advances on these algebraic degrees. So Mateusz Michalek, Monin, and Wisniewski found new results on the maximum likelihood degree of these models. So they showed that the maximum likelihood degree of these models, the number of complex solutions to this problem for a generic linear space, is given by the first row in the triangle of Schubert's numbers. So they published a paper called The Maximum Likelihood Degree, Complete Quadrics, and a C-star action, where they solved some old problems, and they circulated this paper at the beginning of last year, and it just appeared in the journal I mentioned, of which I showed you the picture. Now then, what happened in 2020? Early in 2020, COVID happened. The pandemic started. We were all locked up at home, and we took this as an opportunity to try to bring students and postdoc together. And I circulated a problem list, and the problem list was called 3,264 questions on symmetric matrices. So then many young people got together, worked on various problems, and this led to this collaboration project, of which this is the logo. There was a call for papers with the submission deadline towards the end of last year. And so these papers that resulted in this are all collected now, and this will be published very soon in this Italian journal, Le Matematiche. It's a Sicilian journal. So, so this is a collection of, I think, 14, 15 articles that make nice advance on various questions about symmetric matrices, including the ML degree and the degree of semi-definite programming, and lots of related questions in algebraic geometry that was inspired by this excellent paper by Michalek and collaborators. So I got involved myself in working with some students. So I produced, collaborated on 3 of these articles. So these are 2 students. Claudia is a student in Germany. Jelena is a student in California. Then Arthur is a postdoc who works on tensors, the kind of things we discussed in Ibadan. Henrik is a numerical analysis student. He's not my student. So we wrote a paper on Jordan algebras that I'll tell you about. And then again, with these 2 young people, there's another paper where we deal with a range of tangency questions for conics and quadrics in 3 space. So for example, in this picture, we can say how many quadratic surfaces are tangent to 2 given quadrics, pass through 2 red points, are tangent to 3 black lines, and are tangent to 2 blue planes. So there are 9 constraints altogether, and the answer is 3,712. And we discuss here realities. So we were hoping, our big goal was to show that there's always a fully real instance. We were only able to do this in a few cases, but these are 3 of the 15 articles in this the Mathematica volume. So I'd like to tell you a little bit about the 2 others, and then we're going to wrap it up. So a bit more on likelihood geometry. So a subspace, an LSSM, and Sn is a point in the Grassmannian. So this is the Grassmannian of m-dimensional subspaces in space of symmetric matrices. We're only going to be interested in regular subspaces, those that contain an invertible matrix. And once there is an invertible matrix, those are dense. This allows me to define the reciprocal variety. So the reciprocal variety L inverse is the collection of all matrix inverses, X inverse for all invertible elements. And then I have to close this up to get a projective variety. And well, if a projective variety walks into the door, the first question is, what is your dimension? The second question is, what is your degree? And then you might ask questions about singularities and equations and things like this. So the algebraic degrees, we're interested in the intrinsic algebraic complexity of solving the optimization problem in statistics is the ML degree. So this is where we look at the likelihood function on L, the number of complex critical points, and the reciprocal ML degree is the number of complex critical points on the nonlinear variety L inverse. Here, this is independent of the sample covariance matrix, provided it's generic. Moreover, these degrees are invariant under the congruence action on the change of basis on quadratic forms. So here's one theorem. The ML degree is always bounded above by the degree of the reciprocal variety, and the equality holds for generic L. And then, as I said, Michalek and I'll study this, and they're given by the first row in these kind of diagrams. One more question. How should you multiply symmetric matrices? Well, it's a stupid question, right? If you have 2 square matrices of the same size, you just multiply them and you get a square matrix of this size. But the problem with multiplying symmetric matrices is that in general, you don't get a symmetric matrix back. So what I mean is, how can you multiply 2 symmetric matrices and get a symmetric matrix back? Well, what you could do is you could average the 2 matrix products, right? Because matrix multiplication in general is not commutative. X times Y is not the same as Y times X, right? Whether you first put your socks on and then your shoes on is not the same as whether you first put your shoes on and then your socks on. So matrix multiplication is not commutative, but you could average. And we're going to do this by fixing an invertible matrix U, and we're going to define an algebra structure on the space of symmetric matrices as follows. So X times U is the average of XU inverse Y and YU inverse X. If U is fixed, we're going to drop the subscript. Now, this is a bilinear operation. It's commutative by definition, and the unit, multiplicative unit, is U. However, this is not associative. So this is an operation, a product that's commutative but not associative, but it's almost associative. Namely, the following axiom holds: X times X times Y is the same as X times XX times Y. And this blue axiom is the axiom for a Jordan algebra. So a Jordan algebra is the natural algebra structure on symmetric matrices. Just like Lie algebras appear when you look at skew-symmetric matrices, Jordan algebras appear when you multiply symmetric matrices and you want to get a symmetric matrix back. Who cares? Who should care about such a weird commutative but not associative product? Well, it turns out people do in physics, in statistics, and in optimization. So this is the paper that introduced Jordan algebras for the first time by Jordan, Van Neumann, and Wigner. So they published in 1934 a paper called On an Algebraic Generalization of the Quantum Mechanical Formalism. So they were trying to put quantum mechanics on solid mathematical foundations, and in the course of doing so, they invented Jordan algebras. And most of the literature on Jordan algebra still lives from this interplay with physics. It really came from mathematical physics. Statisticians discovered this in the 1980s. So Annals of Statistics, the most prominent statistics journal, had this article by Jensen in 1888, covariance hypotheses, which are linear in both the covariance matrix and the inverse covariance matrix. Remember, L and L inverse. We have linear constraints on both. In optimization and semi-definite programming, there was a paper last year in math programming by Permenta and Parillo that says dimension reduction for semi-definite programs via Jordan algebra. So the symmetries expressed by Jordan algebras are used by the optimizers for dimensionality reduction. And dimensionality reduction, as all applied mathematicians know, is crucial for methods to scale. So we see that this weird product, the Jordan algebra, is not just a weird thing, but people use this in all kinds of contexts. So one theorem that we proved in our paper is the following. So given an LSSM, a point in our Grassmannian, and given an invertible matrix in L, the following three conditions are equivalent. A, the reciprocal variety is again a linear space. So both L and in L inverse are linear spaces. That is equivalent to saying that L, the linear space, has the structure of a subalgebra of the Jordan algebra. So it is a subalgebra of the Jordan algebra given by you. And once that's the case, then L and L inverse are equal up to congruence, namely we have this relation. Okay. So this is in this paper called Jordan Algebras of Symmetric Matrices. Here's a little example to test our understanding. So if M and N are 4, so here is a symmetric 4x4 matrix that has a 4 entries, X, Y, Z. So this describes a 4-dimensional space of symmetric 4x4 matrices. Here's a different space. All I'm doing is I'm changing the sign on the middle two W's. One of them satisfies this property. One of them violates it dramatically, and you can check. Right? It turns out that this one is a Jordan algebra. This is reciprocal is again a linear 3-dimensional space, while here the reciprocal is nonlinear. It's an interesting irrational threefold in P9. Right? That's nonlinear. So time is up. So I said there was a list of 3,264 questions. That was actually a lie. I just used this number because I like this number, as did the people in the 19th century. Actually, my list had only 65 questions. Many of them are now answered in couple months, you can read all the solutions in Le Mathematicae. So somewhere out there, there's still 3,999 questions for you to find and to work on. And with that, I thank for your attention.